research assistant at the robotics team here, and also staff working at IT department. I'll be your instructor today. Our professor is actually attending a conference in Europe. So this class and the next class, I'll be the instructor for you. So in this class, what we're going to do is DH table using MATLAB's robotics toolbox, but we'll be doing for a 6 degree of freedom. So I'm aware that you guys have already done the 3 degree of freedom in robotics toolbox last time in MATLAB. If you have any questions regarding those, we can go over that now, and then we can continue with 6 degree of freedom. So is everyone okay with the 3 degree of freedom using robotics toolbox? Or do you want me to go over one more time? Alright, let's have a quick look at the robotics toolbox and its commands for the 3 degree of freedom. So I'm going to create a two-dimensional robotic arm in robotics toolbox. By the way, why are we doing this DH table? Can anyone explain? Why are we doing this DH table? So what is forward kinematics? Anyone? What is inverse kinematics?
To translate the point or rotate the point on the particular.
Yeah, those are transformations.
Yes.
So when you're talking about manipulators, there are basically two things that you need to calculate: forward and inverse kinematics, right? So when you have a set of joints that needs to be turned into a specific angle, then you need to calculate what will be the end effector positions in a three-dimensional space. That is forward kinematics. So imagine your arm, right? And how many joints we have here? 1, 2, and 3, 4, right? So if I'm going to turn my first angle to a certain angle and the second joint to a certain angle, and the same with the third and fourth, we should be able to calculate what will be the end effector position in three-dimensional space. Am I right? So this is the forward kinematics. So given the joints, we calculate the XYZ of the end effector. And inverse kinematics will be, again, definitely the opposite of forward kinematics. Given the XYZ, we calculate the angles of each and every joint of the robotic arm. So the reason why we are doing DH is because it simplifies the calculations, and it will be it is a convention that we use to build a matrix, the rotational matrix, so that we can calculate the angles and the XYZ values that are required for the manipulator. So let's have a look at the two-dimensional planar manipulator. I'm sure you guys must be aware of planar manipulator at this moment. So what is a planar manipulator? A planar manipulator just moves in a plane, only in 2 dimensions. So either xy or yz or zx. So not in 3 dimensions. So let's take a look at the DH notation for that planar manipulator. How many degrees of freedom I have here? 2. So it's a 2 degree of freedom planar manipulator, and it will operate only in x and y axis. And I have θ1 for the first joint, and θ2 for the second joint. Okay. So if you are asked to calculate the forward kinematics, so let's say you have a question: what happens if I set θ1 to 30 degrees and θ2 to 45 degrees, and I know the link lengths here, which is A1 and A2. So will you be able to find what will be the position of the end effector? Yes, right, using forward kinematics. So we can solve this in a geometric way using trigonometry. You can create triangles here, and then you must have already done this in maybe your second chapter. So you will have x is equals to A1 cos θ1 plus A2 plus θ1 plus θ2, and same with y. Right. So this is a pretty simple equation because the manipulator itself is very straightforward and simple. But when you are talking about manipulators that have 6 degrees of freedom, or they are operating in 3 dimensions, so the equations will be getting more complicated, and geometric way is always not the best case to solve the equations to find the end effector positions. So using the DH notation, we will be able to get the parameters required for each and every joint, the 4 parameters for every joint. Can you tell me what those 4 parameters that we use in DH table?
A, D, phi.
A and D, alpha and theta. So just using these 4 parameters for every joint, we can construct a rotational matrix, a homogeneous transformation matrix, and we can use that particular matrix to calculate the forward kinematics and find the x, y, and z values no matter how many joints you are given. Are we clear at this point? So let's build that using our toolbox. So does everyone have Robotics Toolbox installed on your computers? If not, just download right now. The first command that you need to know in Robotics Toolbox is the link command. Using that, we will be building links of the manipulator, and then we will be using a serial link command to build the manipulator. So take a look at the DH table for this manipulator right here. When you are filling the DH table, what is the first parameter that you always fill?
Variables.
Variables. So what is the variable for the first time?
Theta 1.
Theta is our MLE joint, so that's our variable. Theta. And for a variable, how do we notate it?
Star.
We use a star mark because the value changes always. And same with the second joint, we have theta 2 as a variable, so we fill theta 2 here. So z-axis will be coming out of the plane here, and then you can take x-axis this way. Have you guys done this DH table before for this manipulator?
Yeah.
Alright, so let's just quickly go over this. So you will have A1 and A2. So these will be zeros, and we only have link lines, A1 and A2s. We don't have displacements with respect to z-axis. So, any questions with the DH table? So we are going to use that DH table and use the Robotics Toolbox command and see how we can build a manipulator. So for the link length, for the link 1, I'm going to use L1, which is my variable for link, and then I'm going to use the link command. So the link function actually takes the parameter, a matrix parameter. So in the matrix, I'm going to enter 4 values. So the 4 parameters that we have here, and also one additional parameter that defines whether it is a revolutive joint or a prismatic joint. And the series that we need to follow here in Robotics Toolbox is not A alpha D theta. In MATLAB, the sequence is D theta A alpha. So that's how you're going to enter the parameters in sequence. So the value of D for the first link is 0. So 0. Let me see if this is theta D or D theta in the sequence. Was it theta D last time when you had done this, or is it D theta in the sequence? D. How are you guys doing this? Does anyone have the handout?
It's correct.
So D theta alpha is correct?
Yeah.
All right. So for link 1, I'm going to use the link function, and d for the first link is 0. Theta is a variable, so we are not going to give any fixed values, so we are just going to keep it 0. A, let's say we have some values for A here. Let's say this is 3, and this is 5.
Oh, sorry. Should be theta d a alpha.
Theta d alpha is the convention. Oh, thank you. Alright, so still the same. Our theta here is 0, and d is 0. A. For A, A1 is equals to 3, alpha 0, and our joint is a revolute joint, so the last parameter will define whether it is a revolute or prismatic using zeros and ones. So I'm going to keep 0 here so that our link will be a revolute joint. So that's link 1. We can do the same thing for link 2 and just change the value for A, which is phi in our case. So,
excuse me.
Yeah.
Enlarge.
Enlarge.
Yeah.
Where do I have to save for this? Is that clear?
Yes.
All right.
Thank you.
No problem. So this is our link 2. So now we have our two link variables L1 and L2. We can use the serial link command to build a manipulator here. So I'm going to call this a manipulator, and then use serial link, and then pass the links as variables here. So there you go, that's your DH table. So now you have the DH table, you can use the function fkind to find the forward kinematics equations. So that actually makes it much easier for you to solve forward kinematics equations for big manipulators. So I'm going to just pass my first variable here, man, and then the second parameter will be a matrix of the variables that I have here. So the variable for the first joint is an angle, the variable for the second joint is an angle. So let's see what happens if I turn this angle to 45 degrees and turn this angle to 60 degrees. Where will be my end effector? So I'm going to pass the values here in radians. So when I'm talking about 45 degrees in radians, it is pi by 4. And then 60 degrees for the second one will be pi by 3. So here you can see that 2.241 and 8.365 are the xy values for the end effector when that particular joint is turned to a specific angle. So go ahead and do it for a 3 degree of freedom planar manipulator. I'll be coming to each and every one of you and see if you have any
Is it
questions.
possible to write the command in a script so we can follow you? Because we lost the previous command, so we cannot follow you.
Sure. So I'm not going to execute it, but I'm going to write it just for your sake. So that should be it. Fill the values of theta, d, a, and alpha in Q1, Q2s with any value that you want. Before you actually do the command, please create a DH table for a 3 degree of freedom planar manipulator, in a paper. Then do that for
No, I was gonna let him know
I did that anyway. So add one more.
I was doing it over here, and I was straight out of nature. But
You don't need to do this, you just do it right here. I'm just writing commands.
I run this. Is this undefined? No, I wrote this.
Maybe you didn't have the robotics report. So you can use the robotics report first. If you have already downloaded, it will go to the map. Yeah, so I think you have already downloaded. I just wrote that data here because you need your instrument. So you need an instrument, you need a and then to the values.
Any DH0 or
Yeah, you need the instrument
based on the
based on for a 3D geometry they are
I just closed it.
Awesome, yeah.